All right. Let's get started. Okay, so we're going to pick up where we left off last time. We're talking about these simple neural networks. So if you remember, we had something that looked like this. Okay, and I had written this equation. I1, comma, I2 is equal to W11 I1 plus W12 I2 equals L. And this is replicating, right, our regular old linear regression. Okay, but I'm going to modify this just a little bit. Okay, we are going to add one term right here, which is A. Okay, so A is known as the activation function. And this allows for nonlinear transformation of the inputs at each node. Okay? So, common activation functions. So this includes the identity, or also known as linear. So this looks something like this. F of x is just equal to x, okay? And so if I were to plot the transformation of this data, it would just look something like this. And the idea here is that if I'm using the identity or linear activation function, then that equation basically looks exactly the same as a linear regression, okay? But we can do other types of transformations as well. There's the step / binary step. So this looks something like this. F of x is equal to 0 for x less than 0, and 1 for x is greater than or equal to 1. So this might look something like this. Or let me use a thicker. This might look something like this. This one looks like that. Okay, so basically here the transformation would change my x inputs into some kind of output of just 0 or 1 for L. Pretty straightforward so far. You've got logistic. This is one that we have seen before, where f of x is equal to 1 over 1 plus e to the negative x. So this one would transform to look something like this. Oh, hang on. Where that would be at 0.5. But the idea is you have some kind of sigmoidal shape, right? And so you are transforming your x's into an outcome of somewhere between 0 and 1, which we were treating, right, as like a probability in the context of our problems. Yes.
On this binary function.
Yes.
Is it 1 for x greater than 1 or x goes to 0?
Oh, yes. Thank you. I didn't even notice that. Yeah, that's right. So it should be greater than or equal to 0. Yes. Good catch. We have tan h. So this looks something like this. E to the x minus e to the negative x divided by e to the x plus e to the negative x. And the shape of this looks kind of similar. Except you go between -1 and 1. And so tan h is actually a fairly common one that's used in a lot of machine learning algorithms, and probably the most commonly used one is known as the rectified linear unit, or the ReLU. And this is f of x is equal to 0 for x less than or equal to 0, and x for x greater than 0. And this looks something like this. 0, 0. Okay, so these are all sort of fairly common activation functions. And again, kind of the whole point of this is when we think about all the different structural forms that we've been looking at to address specific types of problems, the idea is to generalize that approach where I can just like plug that into this A in order to do different sorts of like nonlinear transformations. And so it turns out that if you go from inputs and you have transformations and stuff happening in the middle and then outputs on the other side, you can apply these activation functions as you go from layer to layer in succession and be able to get a lot of flexibility and fit highly nonlinear patterns to get ultimately your output. And that's partly why a lot of these approaches are so powerful. It's not even necessarily specifically, this choice of an activation function, but that by having different types of activation functions, you are able to give enough degrees of freedom to go from any set of inputs to like any set of outputs that you're interested in. Okay. Any questions about the activation functions? So let's continue on. And now we'll look at a multi-layer perceptron. Okay. So we're going to have I1 and I2 as before. And we're going to have some output P. But in between these, we're going to have another layer, L1, L2, L3. So this will be W11, W21, and W31. And this will be W12, W22, and W32. And then each of these will be V1, V2, V3. Okay, so this is known as a feed-forward neural network. This is also known as a multi-layer perceptron. Okay, who can tell me what is L1? How would we calculate L1?
I1 times W12.
Yep. W11 times I1 plus W12 times I2. Okay, and that is just these two that are going into my L1, right? Missing one thing, we just talked about it. Yes, activation function. So I'll just notate that as A11 as the activation function pertaining to L1. Okay, and so similarly, we can figure out what all these guys are. So that would be something like this. A13, W31, I1 plus W32, I2. Okay. And how would I calculate P?
V1 times L1
Yep.
and activation function for
Yeah, so I'll have activation function A2. It'll be V1, L1 plus V2, L2 plus V3, L3. So as far as like the actual connection of a neuron to a particular node, we all know how to do that, right? This is just like a simple linear regression, or linear regression with some kind of transformation if you want, right? And kind of the power behind the combination of all of these things is you are giving lots and lots of flexibility. I take all my inputs, I go through this stuff that's happening inside with all my transformations and weights and everything, right? And the more weights, right, or kind of like the betas, the more parameters that we have, the more flexibility that I have, right, to get to my final answer. So this is our input layer. This is our output layer. And this one is known as a hidden layer. So the idea here, as you can probably imagine, I can introduce these hidden layers, transform the data. I could have 2 hidden layers, 3 hidden layers, and continue to transform the data to get to my sort of output. And then as far as each hidden layer, you can have, this one has 3 nodes or 3 neurons. You could have 4 or 5, however many nodes that you want. And so the more layers and the more nodes that you have, the more flexibility you are allowing the model to go from your inputs to your outputs. And so, yeah.
Keep going.
So what might happen if you have lots and lots of nodes and lots of hidden layers? Are you going to answer that?
Well, I was going to try and answer and then I
Yes.
But if you have lots of hidden layers,
Yeah.
then which means you have many different relationships from the input layer to the output layer. So you could have the impact or the relationship between the input data and the output data could be super weak because it gets moved, it gets transformed so many different times.
The more flexibility that you provide the model, the more, let's say, that the model is able to move from the inputs to the outputs, the closer it will be able to move from the inputs to the outputs. And so when does that become a problem? This is a concept that we've been talking about a lot, right? Overfitting. That's right. So if you guys remember back to our sort of fundamental diagram, right? So model complexity, total error, right? So the idea here is that you can introduce lots of flexibility here, but you potentially are leading to things like overfitting. And so there's that balance about how you set up your neural network in order to try and get sort of the best out-of-sample predictive ability as possible. Okay, and so, yeah. Yes.
So the activation function that you use, and there's 3, the linear, the binary, and then the logistic, are the 3 types of activation functions?
No, there's tons and tons and tons of
Well,
activation functions.
So regardless of the types or number, are you always using the same activation function for each layer or for each node, or are you using different activation functions?
So you can use any combination of activation functions you'd like. So anytime you see this A11, A12, any activation function, you have different choices about putting activation functions in. Generally speaking, you will usually pick one activation function. A lot of a lot of the functions, when you're doing this in practice, just say, oh, what activation function would you like to use? And it applies that activation function sort of throughout. You can also, there's probably ways that you could do it by layer as well. You could do one activation function for one layer, and if you have another layer, do a different activation function. Generally, you should also think about the type of output that you want, because that can help dictate the type of activation function. Right, particularly if like you have a binary outcome, at the very least, probably the last activation function that you want to use is the step or the binary.
Do you, for each layer, let's say you select a different activation measure for each layer, your choice of which type of function to use is based on the observed relationships of the data?
No. Well, in some ways, yeah. But a lot of this is kind of a black box, right? You could have all these layers, and we don't really think of these in terms of like relationships, in the sense that like these weights, which might be representing like coefficients in a linear model, like they're doing all these weird transformations to like all these intermediate nodes that don't really mean anything. So in general, or in practice, the way that I would apply activation functions would be select common activation functions, run through the model, see how well it does in terms of like predicting, and then try a couple other activation functions and see how they compare, and then that should inform kind of the best. Like you would want to use basically the activation function that performs the best for out of sample prediction. Yeah.
So let's just say we have a circumstance where we only care about prediction accuracy.
Yes.
We don't care about
Yep.
anything else. And you have like a set of input variables which you could choose from, and you basically have an infinite number of nodes or layers that you could use.
Yes.
I guess like how do you kind of go through the process of narrowing down how many layers do I want to use?
Yeah.
How many nodes do I want in each layer?
Yep.
How many inputs do I want to use? All those questions you need to kind of.
So how many hidden layers?
Obviously, cross-validation is helpful in that, but when the problem is like not just how many layers, but also how many nodes in each layer, how many inputs, it becomes
Yeah, absolutely.
a little bit of a bigger search space.
And actually, the way, because there's so much flexibility in these networks, people typically use these like rules of thumbs, general rules of thumbs to determine the number of hidden layers and the number of nodes. And then you don't necessarily need to mess with them when you're doing the cross-validation. Because what happens is, okay, where do we actually have flexibility in the model? So I go from my inputs to my outputs. I can choose the number of hidden layers. I can choose the number of nodes. And then I can set values for the weights, okay?
And you can also choose the number of inputs as well.
Yeah, although generally speaking, I would think of this actually more in the line of like the ridge and lasso regressions, where we would just give it all the inputs and then let it deal with it.
Okay.
So you set up your network.
So more inputs is generally always better, I guess.
Yeah, generally speaking. And the power of this is, the way we would do this before is inputs to outputs, cross-validation procedure in order to modify some aspect of the model, right? And with the neural networks, you can just have the cross-validation change your parameter values to give the best out of sample, as opposed to having it change the number of hidden layers and the number of nodes and the parameter values. So once you have this part of it set, you just hands off, let the cross-validation figure out what the best values of all those things are. And so, like, suppose you had too many nodes or you had too many hidden layers. One thing it could do is in the cross-validation process, maybe it would just change the weights going into L3 to like 0, right? And so that's like almost internally a way that the model could figure out how to like get rid of nodes or entire layers to some respect. So, hidden layers. Number of hidden layers, generally, these are rules of thumb. So 0 represents linearly separable, whoops, that's not how you spell separable. Linearly separable functions. 1 approximates any continuous mapping in finite space. And 2 plus represents arbitrary decision boundaries. 2 arbitrary accuracy with correct activation function. Generally, for a lot of stuff that people do, like one hidden layer is going to be good enough. Number of nodes. Okay, again, rule of thumb. Size of input layer greater than hidden nodes greater than size of output. Hidden nodes, I've seen a couple different heuristics. So number of hidden nodes equals to approximately equal to 2/3 the number of input nodes plus output nodes. I've seen hidden nodes less than 2x input. And then number of nodes equals number of samples divided by alpha times number of inputs plus number of outputs, where alpha is between 2 to 10. But generally speaking, right, the more nodes that you have, the more that you lead to overfitting. And so these are, again, just rough heuristics that people use, but just keep in mind that there is a bit of arbitrariness to this because a lot of the flexibility that you are affording the model through adding these nodes can get sort of taken care of by modifying the parameter values that will happen automatically when you're doing like cross-validation. Okay. Give everyone a second to digest, and if you have any questions, we can chat about it. Otherwise, we can jump over to the code.
I'm trying to think of the applied element of this to like energy data or something, right? Like
Mm-hmm.
how does this get me better results, whatever that outcome I'm seeking, than just doing like a predictive model? Is this more like relevant to
Yeah.
the
So I can give
decision, or
So I can give you an example, actually very salient to me, that I just learned about this week. Yeah, so I do a lot of EV grid work, and a lot of what I do, or some of the stuff that I do, we look at like, oh, what is the emissions impact of electric vehicles? So the idea is like, I plug in an electric car, and some power plant somewhere out there is like turning on or ramping up. And then you have to figure out what power plant is doing that. So in power systems modeling, this is known as a dispatch model, where you're simulating how power plants work. And it's very complex. So the way this works is like it's a big optimization problem where a lot of people are turning on electricity appliances, and then the optimization says, this power plant turn on because you're the cheapest, and then this power plant turns on because you're the next cheapest. But then you have to do all these things like you have to think about where all the power plants are, how the electricity travels through the network, how they can like import and export out of like balancing areas. It's a really complex optimization problem. So these larger scale dispatch models that you might be running at like a state level or a national level, like I've spent years building these, and when you run the model, it's got to process all of this data about the power plants and about the like electricity load, and then the output of it is it tells you how the power plants are operating. Okay. And to run a national level model, I'll give you an example. So I used to use the Lawrence Berkeley National Labs supercomputer with like, 10,000 CPUs or whatever, and I could do these runs in a couple hours. And we've simplified the models a lot. We can run them locally, and they take maybe 2 to 3 days to run like one national level run. So one thing that I just found out in the power systems community is once you've run these models a couple times, I can take all this input about like electricity loads and power plant data, and then I can take the output from my dispatch model, and I can just put it into a machine learning model like this. And then anytime I have new input data, like I want to change loads, like I want to introduce like EVs onto the grid, I could change my inputs and then predict the output based off of the trained model. That takes like milliseconds to run, right? Compared to trying to, like, that would take milliseconds to run on my laptop compared to using a supercomputer for like many hours. So the thing about this is if you have some kind of input and some kind of output, these networks that do all this like crazy stuff in the middle that we don't really know what's I mean, you do know what's happening, but in more complex models, like no one bothers to look at all these like middle hidden layers and stuff like that. You can do really, really complex things that that would be very difficult to do otherwise. Yeah, and that's like a lot of the more revolutionary things that have been happening in like data analysis and training, like artificial intelligence. That's all coming from stuff like this, where the middle things are kind of like black boxes.
Okay, that makes sense.
Yeah.
Now I
So
wanna ask
so
how
like
you do
the
that.
so yeah, I mean to think about it in the context of like this course, right? We are a lot of what we've been doing is we go from here to here in like a particular way, right? We think about doing it in a linear regression, doing it in like a logistic regression, or doing some nonlinear thing going from through like splines to go from here to here, right? This is the generalization of all of those approaches kind of put together, where our ability to do any sort of interpretation of like how the transformation is happening kind of goes out the window a little bit, because as soon as I do like a ReLU activation function here and then another one in another hidden layer and then going to my output, I don't really have any idea of like what's happening inside the layers, but I do get the right answer more often than using a different type of model. And whereas a lot of the approaches that we had talked about, up to now in the beginning of class, you start to run into constraints about like the types of problems that they can tackle, the scalability of those problems, like kernel regression and even doing splines for like nonlinear fits. You're gonna start running into like computational complexity issues once you're getting to data of a certain size, and this like fairly simple approach, right, where you just have parameters and then this like simple activation function is really well equipped to deal with that. Yeah, that's why this area has been such a popular field over the last decade. Yeah.
So basically, we don't decide where it goes to hidden layers, right? It's already built in.
You can choose the number of hidden layers and the number of nodes.
Oh, that's just the number parameters there, but we don't really know what. Well, I guess when we get the results, we don't really know those results come from what type of model in the middle, right? And then I guess my question is, if we have the area look like that diagram, then we're actually assuming the I1, I2 follow a path through R2, get to the P outcome.
Yeah.
Then, well, basically, if we know what's happening in the hidden layer, that has to build on our theoretical framework, we're assuming there's a transition along the path, right, that cause or whatever prediction has been happening along this line. But we lose that information, so basically we lose the theoretical models in the middle piece.
Yes. Yeah, exactly. So the like foundation of like why I would do like a linear regression, because I think the functional form is of some way. Any inferential stuff doesn't really exist in the machine learning world. It's all about prediction. Yeah.
And this also doesn't take the mediating variables into consideration because everything just.
Oh yeah, this is not. Sorry. Okay, this is not a causal diagram.
No.
This is not a DAG. Yeah, it's just so these are not causal relationships or anything. These are just. It's just a diagram to show how they're connected.
Yeah, I just want to
Yeah.
see that limitation.
Yeah.
Bound.
Yeah. So taking a step back to this idea these two approaches where we say, do we care more about prediction, or do we care more about inference? This is like so far into the prediction world, right? And yeah, I mean, so philosophically, I think I would personally be more leaning towards this type of thing because from my perspective, like you can develop inferential models that have that demonstrate causality very well, but that do a bad job at predicting an outcome. And to me, I kind of question the value of that. So if you make a model that says X leads to Y, but your ability to predict Y is like not very good, then how much do I trust like the other elements of the model that are telling me this like relationship? So, but that gets into a whole debate about like prediction, like parametric approaches versus non-parametric approaches, prediction versus inference, and we won't go there. So, okay, why don't we dive into the code real quick? All right, so load in a couple packages, and we are going to load in a data set called defaults. I believe we've looked at this data set already, but let's just let's go over it in just a second. I'm gonna quickly do some data manipulation so that it'll recognize these as numbers, and I'll talk about this in just a second. Okay, so I'll jump back here in just a second, but let's take a look at our data set. Pretty simple data set. Oh, maybe we haven't used this one yet. We used a credit limit one. Okay, this one is simpler. There's only 4 variables, okay? Default, student, balance, and income. In the version before I did some modifications, default and student said yes and no. So I simply added these 2 lines of code to change the yes and no to 1s and 0s. So that is a numeric value that it'll be able to use. Okay, so jump back to the code and let me do a quick summary of this data set. So, does it tell me? No, hang on. So there's 1,000 rows. We can see the balances, the income, 10,000. So of the 10,000 data points, about a little less than a third of these are students, and then only 0.033 have the status of default. Okay, so that means like 300 people out of 10,000 have that default value. So we'll keep that in mind as we go through this. I'm going to scale the data. except for the actual outcome value. And then I am going to create a training set and a testing set. I'm just going to divide, or I'm going to take 70% of it to use as training and 30% of it to use as testing. So we're going to do this. Okay, so all this is doing is I am doing sampling of my default sort, only 70% of it, so that's going to be my training set, and then the testing set, I have this little minus to indicate everything that's not there. So now if I look at the data, I should have default.train. Oh, I didn't run it. Hang on. Default train, 7,000, and the other 3,000 are going to be test. Okay? And then all of these values are now scaled, and then this is left as zeros and ones. Okay, so, I need to load in this guy, neural net. So this uses the function called neural net, defaults. I'm going to use my training data as my data input. I'm going to have one of the parameters of the function specifies the number of hidden nodes. So it'll be 2 and 3 as the number of nodes in the layers. And I'm going to use a logistic for my activation function. And my output is not going to be linear. So I can run this, let it go, and let's see what happens. Okay, so hang on. If you look at the code really quick, so you'll notice that I have my input layer here, my output layer here. I have 2 hidden layers. The first hidden layer has 2 nodes. The second hidden layer has 3 nodes. Okay. Where's my mouse? Here we go. So that's specified by 2 and 3 here. Okay. So the values for L here can be determined via the weights using the equations that we had in the notes. So if you wanted to, you could go in and calculate these. You'll notice there's actually one extra thing here, which I didn't talk about. So these blue nodes, so those are called hidden nodes, I think. But they're basically like intercepts. Okay, so there's an extra dimension that that it's allowed to include here. And so these help give even more sort of degrees of freedom into your model.
Is that additive to the?
Yes. Yeah. So it would be like A11 W times I, close that off, plus these values. Yeah. Okay, and so when you plot it, this gives you the structure of that, right? And so you could go in and you could figure out what values these would be, but they don't really mean anything. They're just these intermediate layers that are trying to get you to your output. Okay? So, how well does this function? Oh yeah, go ahead.
What is the reason to scale the data?
Yeah. I think, so I'm not positive, but I think the performance is generally better and faster when you scale the data, but you don't have to. Yeah. Okay, so we can use a function called compute, which is the same thing as predict, but this is for neural networks. They use compute. So if I go ahead and run this, it will give your sort of predicted values. And we were doing logistic transformations, and so these predictions represent probability of your outcome. So probability of defaulting. Okay? And okay, so what I'm going to do, I've generated my predictions, and then into my test set, I'm going to create two columns. I'm going to create one column called probability, which is the set of predictions I just made, and then I'm going to have it predict whether or not the person defaulted. And I'm just going to say, if the probability is more than 50%, then we'll assign them a 1 for they did default, and a 0 if they didn't. So if I run this and now take a look at default.test, what we see is there is a prediction in terms of the probability that the model thinks the person defaulted, and then that prediction of 0 or 1 based off of if this value is bigger or less than 0.5. And actually we see 0 for at least all the ones that you can observe right here. But let's see how well the model actually does. So
Why? I'm sorry, I might have missed it. Why is it in the student column there's negatives?
because we scaled it.
Oh, okay, yeah, okay, sorry.
So you can use this to determine the mean squared error. And actually, you know what we should do? We should look at the overall error. Right, and so let's see. So how would I calculate the overall error between my actual and predicted outcomes?
Sum of actual times predicted.
Yeah, the number of times you were wrong, which is close to what you were saying, but if I do,
Just count when something doesn't.
but if you do that, if I just add up this and minus the sum of this, like if this was a 1 here and this was a 1 here, then it would be then the total error would be 0. So you have to do one at a time and then sum, not the absolute value. Yeah. So let's try that really quick. So sum. Actually, does anyone know what? How do you do absolute value? Is it ABS?
Yeah, it is.
Okay, absolute value of default dot test dollar default minus default dot test dollar predict. Okay, so 80. So this should be divided by n row default dot test. 0.26. Okay, so this has a 2.7% error rate.
Well, is this, you just did the same thing? Because it's absolute value, you square it.
Oh
It's the
yeah.
same exact
Well,
value.
it's because it's ones and zeros. Yeah.
So you have to, don't you have to do?
No, this is right. This is
Yeah,
it's the
you
same
do
thing. Yeah. In this case, the mean squared error would be the same thing. Okay. So is this a good model? It's pretty good. Why is it pretty good?
So you're predicting wrong 80 times out of 10,000.
Okay. So it has a it's pretty good because it has a it's 80 out of 3,000 because it's the test set. So we're saying it's pretty good because it has a 2.7% fail rate. So this is one thing that you have to keep in mind. What is the default error rate? If I were to just, no. So if I were just to say 0 for, if I were to say 0 for everyone, if I were just to say it straight up say 0 instead of 1, how many summary default dot test?
Right. More often.
So if I just said 0 for everyone, I would have a 3.3% error rate. So the model is better than guessing based off of, random intuition, because the error rate was 2.7%, but it is lowering this by 20% improvement. Okay, so remember that your error rates should be contextualized to the actual data that you're looking at. Okay. And then, as I've kind of mentioned before, we care about false negative and false positive rates. And so we can measure this by doing something like this. And then false positive rate. Oops. Less than. Okay. So the idea is, so it's false negative if default is 1 and your predict is 0. So if your actual data is larger than your predicted, then we count that. And then for false positive rate, it means the actual is 0, but you're saying it's 1. We count that. So the false negative rate it ends up looking something like this. So we say, so it's more common in this model to incorrectly predict that someone isn't defaulting when they are, and then it's doing better at saying someone who hasn't defaulted is defaulted. So we can actually modify this model to have a preference for one of these two things. And so what ends up happening is I can lower, for example, my false negative rate at the expense of increasing my false positive rate. And your overall error will go up, but you could lower this one more. So like if you were a bank, would you care more about a false negative rate or a false positive rate? Yeah, false negative, exactly. Because you would care more about getting it right to predict that people would default. And so you might tune your model to care more about this than your total error rate. And you're sacrificing your total error rate to lower that. Okay. And so, yeah, so this type of approach lets us do these transformations of our data and be able to do kind of similar types of things that we've been talking about, right, with like a logistic model to get a particular outcome. But very often, these neural networks are going to outperform a lot of the traditional stuff that we've talked about. Right, because at the very least, if I'm doing a logistic transformation, I could at the very least just replicate what a logistic regression would be doing. Right, it could weight things in a way that it would do exactly that, but then it can probably do better because it's more flexible. Okay. Any questions? Okay, so for the last half of class, yeah, I want to lean a little bit more into this and show an example, a more sort of interesting example maybe of some of the capabilities. Yeah.
So just in that comparison, the logistic model, is that basically like this, but with no hidden layers?
Yeah. Yes. Exactly. So no hidden layers with a logistic activation function going to that.
Yeah.
That's exactly what it would be. Yep. So it could, I don't know exactly how, but it could change the parameters here and here to almost ignore this hidden layer, like replicate the input and then have that activation function going in here to match the logistic function. So if the logistic function in theory was like the best optimal model, like this could do that, right?
Yeah.
But it could do more. Okay, so let's talk about one interesting application of this to kind of demonstrate some of the. Oh, sorry. Go ahead.
So I think you mentioned earlier that I think neural networks work better or work in the case where the inputs are greater than the output nodes. Or did I misheard that?
Oh, I was talking about the decision of how many hidden layers and nodes to have. And that is, by rule of thumb, a function of the number of input nodes and the number of output nodes. Yeah.
So there are cases that we could create a neural network that has more output nodes than the input.
Yes. Yes, you can. That is possible.
Thank you.
Okay, so I'm going to show an example. We're going to talk about a specific type of neural network with a specific application that I think is neat, that might not be as useful for everyone. This is more in like computer vision and that type of thing. But we'll highlight some of the power and complexity that you can get to with these types of models.
Real quick.
Yes?
The 2,345 steps, what is that? What is that?
One, right?
Oh, here.
Yeah.
I actually have no idea. This might.
How many iterations it did to figure out
So I might have suspected that, but this seems really high for a number of iterations. But let me double check that, and I'll get back to you. Yeah. So the error rate. So this error refers to a specific type of measurement that you have to calibrate your inputs and outputs. That's the final one that it lands on. I don't know what the default is, but you can specify this. You can change the type of error that you'd like your model to be looking at. Yeah. Yes.
Maybe this is a silly question. Can you give us an example to interpret the weights and input?
No. No one ever looks at the weights. There's no point in looking at the weights, right? There really isn't, because these are like your betas, but betas that go to nothing.
Nothing.
Yeah. So there's no. Yeah. So okay. Like.
Practically, we don't show this diagram, right?
No. Yeah. You
Otherwise
don't.
it reads a lot
No.
more
You
shit.
show the errors and stuff like that. I mean, you can show the diagram. It kind of shows the general structure. It also gives some like ability for people to replicate your work, right? Because if you give the structure, they know how you set up the model. So it's not totally nonsense. But it's not like someone's going to look at this and be like, 2.5, that looks wrong. That doesn't seem
Yeah.
right. I don't know what any of these numbers mean, to be honest. So, all right. So, what is this? And what is this? Yeah, but how do you know? How did you know that?
Because a dog.
Right, okay, but there's like something about this picture that tells you it's a dog, right? Like, okay, cool. Okay, we're gonna get a little harder here, okay? All right, what is that? Cat?
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 Dog.
Are you sure? Okay. What about now?
Sure. Because you haven't switched over.
What about now?
Yeah.
Okay. So keep this in mind. Like, you can look at this blurry image and you can be like, yeah, that's a cat. Yeah, that's a dog. We still know that's a cat and that's a dog, right? And so there are certain characteristics about these images that are leading us to these conclusions that may not necessarily require like 100% fidelity. Okay. What is that?
Is that a global map? It's a dot on South America. What? It's a dot west and then it's Africa or something.
How about now?
Oh, there's a cat there.
It's a cat.
Is it the negative of a picture of a cat?
Interesting. Okay. So that's the original image. Okay. So we're getting to this place. Okay, maybe it was harder to tell here, but you guys saw this and you were like, cat, right? So if I were to reduce this picture in some way, in blurriness, looking at the edges, that type of thing, there's something about the information being conveyed here that still lets us know that it's a cat. All right, so we're going to keep that in mind as we think about convolutional neural networks.
Are we just helping you tag photos for your own?
Well, we'll talk about that. Yeah. We'll talk about that.
It will just turn into a student tagging farm.
Okay. So for the rest of class, we'll talk quickly about convolutional neural networks. This is a class of deep neural network. This is a regularized version of multi-layer perceptrons. Particularly well suited to analyzing grids of data, aka images for classification. Okay, so consider a picture.
Penguin.
Okay. So I'm drawing this crude bird. When I think about this as like data, how would this be represented?
Well,
I'm hearing,
it's a picture.
yeah, it's a picture.
Well, then it'd be the pixels on the picture, and the pixels have a specific data type associated
Yes.
with it.
Okay, it's called RGB. So each individual pixel, so this picture can be reduced down to a set of values, 57, 83, 62, right? So I can turn this into tables of numbers that represent red, green, blue, whatever, that are used as data to create that picture. So I could take this and just input 1, input 2, input 3, and then output bird, right? As my neural network, RGB. And then, well, you could have stuff in between, right? But we don't actually do this. And the reason for that is there's too many weights for a perceptron. It's too big. These images, right, think about how large and how many pixels an image could have. So, convolutional neural networks use a couple processes to reduce the complexity of the image. And we can do that and lose fidelity, but right, you would still be able to tell that a cat is a cat. So, processing images with 3 successive techniques. So 1, convolution layer, 2, pooling layer, and 3, fully connected layer. Okay. Oh, I should choose a smaller example next time. All right, hang on. I gotta fill this in because I'm using real numbers here. So the point of what I'm doing here is I'm taking, let's say, a representation of the data behind an image. So these numbers could be like RGB values in this table. And I am applying what is known as a filter. So this is a filter or kernel. And this particular one is known as a mean blur filter. And what this does is it takes information here, applies it through this filter to get a set of values. Okay, so we're going to apply a filter with a what is known as a stride. So this is number of steps in a direction. So we're going to apply a stride of 1. So mean blur filter applied to this box, which is going to be the first one, will result in 41.6. That is the mean of these 9 values. Okay? And then I'm going to move in one direction. So that's going to be these 9 values. If I take the average of that, that'll be 58. And then I will move in one direction as well here. And the average of that will be 61. Then I will do this. Average of those, 41.8. And so on and so forth. Oops. 63.8, 70.3. So, what do you think happens to the image when we go from here to here? If I were to just take this after doing the mean blur filter and look at the image again. Yeah, so it does slightly lower the resolution, and actually this step often wants to keep the same resolution, so it'll have some kind of algorithm to say, oh, on the outside border we're gonna use some other thing. So, but yes, size of the image decreases a little bit, but the bigger thing is that yes, it's blurring it, hence the mean blur filter. Right? Because you have some sharpness as defined by these pixels, and then I've just averaged them all. So, you know, light brown, dark brown, really dark brown, medium brown, blah, 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 gets reduced into brown. So everything's just been blurred. So image is slightly smaller and blurrier. So the technique is called padding, where they add stuff around it to make it still preserve size. So other filters that you can do, so one of the more common ones is known as the edge filter. So 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. This is called a vertical. There's also horizontal. There is the Sobel. And there is the Schar filter. So it turns out that when you do this to an image, when you apply these filters to an image, that's how we go from the cat picture to the outline of the cat, right? These edge filters are what help you achieve that. And so those black and white pictures, you know, one of those is one of these edge filters, or both of them are different types of edge filters, basically. There are actually algorithms to also sharpen them. So sharpen, this looks like this, -1, 0, -1, 0. So when you see in like TV shows, they're like, enhance. It's probably something like that. Yeah. And then another common one, if you want to blur, this is known as a Gaussian blur. Okay, so why do we do this? These filters can take images, and once applied, you are generalizing sort of characteristics of those images that that the model can sort of latch onto. So actually, if you consider the original image that I showed you guys with the cat and the dog, there's a lot for the model to latch onto, like noise, right? So like something like fur, for example. Well, like both a cat and a dog have fur, right? And those characteristics might be something that you would observe in the data, but by doing this, you can sort of generalize the data to a much larger extent to focus only on characteristics that distinguish like cats and dogs, right? And so, yeah, these filters essentially help to reduce some of the noise that the model can avoid sort of latching onto. Okay. So that is this first step of our convolution layer. So next, we'll talk about the pooling layer. And so the pooling layer is the part that we really care about for reducing the size of an overall image. So here, if I had some image that looked like this, 1, 3, 2, 1, 2, 9, 1, 1, 1, 3, 2, 3, 5, 6, 1, 2. The key elements of a pool is the filter size, the stride, and the filter algorithm. And so the most common ones are known as max pooling and average pooling. So the stride is the same as we talked about before, but in pooling, oftentimes the stride is larger than 1, whereas in the convolution layer, it's usually set at 1. And so the stride is the thing that's really going to help reduce the size. Okay, it's actually pretty straightforward. We're going to apply a max pooling algorithm that's going to look at 2 by 2 elements with a stride of 2. So we're going to reduce this from 16 data points into 4 data points. So my filter size is a 2 by 2. And I'm going to apply max pooling. What do you guys think that means?
Take the max.
Take the max. 9. Let me use the same color. 9. Okay. If my stride equals 2, what's the next step? What would I outline? Top right, yep. So here, so what would my value be? 2. Great. Next guy is going to look like this. Largest value is 6. And last one is here. Value is 3. Cool. So pooling, data reduction, right? And so if you think about the picture of the dog and the picture of the cat, oh, I should do this next time too. I should reduce the size, and you could still tell that it's a dog or a cat, right? The image is smaller. Yeah?
I have a question about like the pooling and blurring when you are working in black and white. So
Yeah.
as an example, like images like Tesla's, quote unquote autopilot, like it is in black and white. And it's in black and white, or at least the cameras are in black and white. Or some of them are because they don't have like less color or less data to have to worry about.
Exactly.
And when you have black and white and you're working in shades, so it's functionally the same kind of approach. You just have shades of
Yep.
like 0 to 1, and that's like white or black.
Yes.
Right? And then, but do you lose like, does color give you more insight into what the actual thing is?
Well, it depends on what you're trying to classify, right?
Okay.
Like if color is an essential element of the classification process, then you probably don't want to get rid of that. But the thing is, yeah, so the thing is, shading can help represent colors a lot of times, but not always. Okay. So if your image depends specifically on color, you probably want to preserve that. Okay. Great. So convolution layer, pooling layer, we can see what's happening in terms of like reducing the image quality and the image size. And going back to those pictures, we can demonstrate that still you preserve enough information to do your classification correctly. So it's okay that we're like messing with the image to make it easier for the model to handle. Okay. So last step is called flattening. So convert last convolutional layer into a one-dimensional neural network layer. Oops. So why not connect all layers? Number of weights grows exponentially. I should caveat that since I learned this stuff and since I've been sort of teaching this, that CNNs, that there actually are versions of CNNs called fully connected networks that actually do connect all the layers. I don't really understand it, so I can't really, I'm not going to explain that. But to give a sense of why fundamentally this can be difficult, and why traditionally it hasn't connected all layers. So consider a 32 by 32 pixel image with RGB channels. Does anyone know how big a 32 by 32 image is? It's very small, right? 32 pixels. So like on a modern monitor, that would be like smaller than a thumbnail, right? It's very small. We'll look at some 32 by 32 pictures in just a second. So just the first input and first convolutional layer would have 32 times 32 times 3, right? So that's the amount of data contained in our original image. Each pixel represents 1 point. 32 by 32 represents all the possible pixels in that picture, and times 3 is for red, green, and blue channels. Okay, and then we did our filter which would result in 28 by 28 by 6. So this is about 14.5 million points. Even prior to the last one, which is the flattening. And so, yeah, the amount of nodes that you would need would be tremendously large, right? Even too big for something like a machine learning algorithm. And so, all this transformation process helps us reduce that down, right? So we start at 32 by 32 by 3 as our input. This goes to something slightly smaller, 30 by 30 by 5 in your first convolution layer. That's an activation function. So this would be like 5 filters with 1 stride. And then from here, 2 filter, 2 stride, you would get to 15 by 15 by 10 in our first pooling layer. And you could continue doing this. And you could reduce, right, the size of your network. Down to something like 400. Okay. So the gist of the neural network itself hasn't really changed. We're really still talking about outputs of classifications with these large data inputs, but the idea is how you reduce an image size in ways that could feasibly be handled by your neural network. And that process is this like doing the convolution layer, doing the pooling layers, and so on. Okay. Any questions about this? Okay, so I'm going to show this example in code here. You don't need to follow along. This uses actually some fairly more complicated packages to run anyways. Actually, it uses a Python backend. But just to show you a little bit about what the neural network is actually capable of. Okay. So let's jump on over to here. So there's a well-known training set for images that we're going to look at. So this uses a package called TensorFlow, which is a common machine learning package in Python, actually. So to do this, to install it, I would recommend installing Anaconda 3. You can look that up, or you can ask me if this is something you're actually interested in, and then install TensorFlow using the Anaconda backend. So you can't do this now, so just follow along, and I'll post this code. So we're going to use some of this stuff. So this data set, I think it's called CFAR. This is a very well-known data set for doing image training. And so we're just going to look at a couple of these. So we've got classifications of airplanes, automobiles, birds, cats, deer, dog, frog, horse, ship, truck. Okay? So we want to make sure that the model, or we want the model to be able to classify images of these things, okay? So obviously the more data that these machines get fed, the better they are at understanding that something is one of these things, right? But we're actually going to feed it not that much data and see how well it does. But yeah, image classification, right? Click on all pictures of streets or fire hoses or bikes or whatever that you guys do all the time. You are just helping model validation, actually, for these image training. And by farming that out to lots of people, right, doing it, it's a manual process, but that's how a lot of these things were originally sort of got data sets to train on. Okay. So so these are 32 by 32 images. Okay. All right. What's this? Frog, car, deer, truck, deer, frog. Yeah. Emu. It's not going to get that specific, unfortunately. Horse, truck. Okay, anyways, you get the idea. But these are like fairly crappy images, right? Very low fidelity. It's only 32 pixels by 32 pixels. Yeah, and we're going to see how well it does. So this is actually the training set. So we are telling it.
So only training out 30 images?
Yes. So we are telling it these things.
It is verb. So it could be cassowary.
Yeah. Okay, so let's run the model. Wait a minute. Did it store? I think it stored the results. Oh no, okay, here we go. Okay, so this is going to take a moment to run through, but essentially it's doing a smart version of the things that I was describing. And it's going to go through these things known as epochs, which is running through the neural network, getting values for my weights, and then looking at the loss function, and then recalibrating the weight. So it's doing this iterative thing. It's essentially doing like a cross-validation update to its parameter values. And so every time it runs through an epoch, one of the things that we would hope to see is a decrease in the loss value and an increase in the accuracy. I don't know exactly what the loss value that this particular model is choosing to use, but the accuracy represents in an out-of-sample test set how many of the classifications that it's getting correct. So what I will say is that these categories are approximately equally distributed in the data set. And so what would my error rate be for random guessing amongst all the classes? There's 4, 5, 6, 7, 8, 9, 10. Okay, 10, right? So if I just guessed everything of like one category, then in theory I would have like a 10% success rate and a 90% failure rate. And so just from 30 images, we can see against a test set that it's getting 60, about 2/3 of the classifications correctly, just from that small set of images. Yeah, so that's image classification using convolutional neural networks. This is kind of a speed run of machine learning. If you took a real machine learning class, you would go into a lot more detail about some of the things that are happening behind the scenes, but at least hopefully you guys have a basic understanding of how we went about going from neural networks all the way to sort of this image classification and being able to actually sort of identify images based off of what's contained in the picture. So yeah, the code will be available, posted online, and if you're interested in this more, happy to chat about that, yeah.
So it took into account the color, not just the shade?
Yes, I believe in this particular one it is looking at color, yeah. And that might help with like animals versus like vehicles or something.
If there was like no white horse in the training data, you think it would detect a white horse? Or
I think it
just
could.
Based on the outline of it?
Yeah, so I think in the outputs, right, there's actually, you can think of this as almost an intermediate step where it has some probabilistic determination for the classification. So if it didn't have any white horses, maybe by color it's saying, oh, we're going to be a little bit more uncertain, but then by like the edges it might say, oh, I'm still fairly certain this is a horse. Yeah.
So we want to specify, we want to train the model based on the edge of the object or the color. Is there a way to specify when we run the model, or do we need to first convert all the images to whatever condition we want to train it on, and then feed it to the model?
Yeah. So you can definitely tell it if you wanted to go deeper into it, you could specify like the filters in each of the layers. This particular one is doing some a particular. It already has some kind of optimized choice for this data set, so we didn't specify that, and it's applying some set of like pre-known filters. But yeah, you can certainly customize that.
So does that conversion automatically then, so we don't have to put more work rather than labeling?
Yeah, exactly. I don't know exactly how I extract that, but well, let me see. Can I so far $test $y? Yeah, okay. So it's assigning categories for images. I'm not sure what I'm looking at here actually. I thought it would be one vector, but apparently it's a lot more than I thought. Okay, but anyways. Other questions? Okay, well, so that's it for neural networks. We will have one last class on Wednesday. Remember, Monday is a holiday. And so on Wednesday, I think what I'll do is just kind of do an overview review of all the stuff that we've covered in class. Well, thanks everyone. See you guys next week.